So sometimes we might be asked to use a normal approximation to the binomial distribution, and there's some conditions that we have to have for this. So n needs to be large, so generally more than 50, but it'll tell you in the question, and p should be as close as possible to 0.5, and the closer the binomial probability of success is to 0.5, the better this normal approximation is going to be. And that's because if p is close to 0.5, what ends up happening with our binomial distribution is we get quite a nice, so that's the probability, this is our x values, we get quite a nice symmetrical, and this is not for very large n obviously here, but we get a nice symmetrical distribution, so the probabilities start off and end up doing this kind of thing, so we get this normal sort of shape, this bell-shaped curve. Okay, so these are the conditions that we need. If we're asked to do a normal approximation, then this is what we need. We need the normal, which has got mean and standard deviation squared variance. We're going to use that rather than the binomial with number of trials n and probability of success p. And these are the formulas that we need to know. So mu, the mean, is going to be equal to n times p. And sigma squared, which is the variance, don't forget that's just the standard deviation squared, that's going to be using this formula, np, brackets 1 minus p. Now don't worry where these come from at the minute, we're just going to use these in practice to see what happens. I'm going to put a square around them, not a square, rectangle. I'm going to put a rectangle around them because you do need to learn those. Okay, let's have a look at an example. So in this example, we've got a binomial distribution. So x is binomial distributed with n 100 and probability of success 0.4. And we're asked to use a binomial approximation to evaluate these. And what we'll do here, we'll use this normal approximation, but we'll also do the binomial and see how close, how good approximations these answers give us. Okay, so the first thing we need to know the mean mu. Well, that's going to be n times p, which in this case is 100 times 0.4, so that's going to give us 40. And we also need the variance, the standard deviation squared, so using that formula, np times 1 minus p, so 100 times 0.4 times 0.6, that's going to give us 24. Okay, and then what we're going to do, we're going to introduce a new variable, y, which is going to be normally distributed, and this is going to have mean 40, and standard deviation 24. And don't forget at this point, this is the standard deviation squared, it's the variance, so sigma, the standard deviation, is root 24. And that's really important. That's, again, we've talked about this before, people generally, if they're going to make a mistake, that's where they're going to make the mistake. Okay, so let's have a look at part A. Part A wants us to find the probability that x is equal to 40. Now, one of the big things we have to remember here is that binomial is a discrete distribution. So there's gaps in the data. There's nothing between 40, 39, 41. In a normal approximation, it's continuous data. So here, 40 does not mean the same thing as it does for a discrete. So 40 is anything between 39.5 and 40.5, because all of those values then round to 40 on the continuous line. So let's have a think about a number line. So a number line here, I don't know, let's go 38, 39, 40, 41, etc. Okay, we want from the binomial x to be equal to 40, so there was nothing either side of these. But for the continuous normal, that's going to include that part of the data. So we do what we call a continuity correction. So converting from a discrete number to a continuous number. So that's going to mean that my y can be anywhere between 39.5 and 40.5, sorry. Okay, and then this is going to be using our calculators, our normal distribution. We're going to have a look at our lower is 39.5, our upper is 40.5, our sigma is root 24, don't forget, standard deviation, and our mean is now 40. And that's going to give me the answer 0.0812925, etc. So I'm just going to use the binomial distribution now and have a look at how accurate that answer is, how good an approximation is. So using the binomial PD, because it's an equals to, the probability that x is equal to 40, let's have a look. So binomial CD, binomial PD, because it's equals to, so that one. I just want a variable because I know the value of x. X is 40, and then n, I'm going back to my original up here now, so n is 100, and the probability of success is 0.4. So 0.081219. So it's not bad. Not bad. Correct to what? 2 significant figures? Okay, let's have a look at this next one, an inequality this time. So part B, the probability that x is greater than or equal to 50. So the first thing we've got to remember to do is our continuity correction. We've got to convert this from being discrete to being continuous. Quick sketch of a number line. This time I want to be greater than or equal to 50. So this is the part that I'm using. This is the bit that I want. So if it was a binomial, which we'll do in a second, I'd do 1 minus everything less than or equal to 49. Because it's continuous, it's normal, this time it's continuous, so I'm going to go everything that is greater than or equal to 49.5, because that would round to 50. So that continuity correction is going to give me this as my normal question. Probability that y is greater than or equal to 49.5. So let's have a look. So we want our normal CD. Our lower is 49.5. Our upper, don't forget now, as long as we're going at least 5 standard deviations above the mean, we should cover almost all of the data. So I'm just going to put 1,000 in there, really high value. Sigma is my root 24. I think that's still in there from before. Mu is my 40. And there's my answer, 0.02623. Okay, now let's check that using binomial. This time it's a binomial CD. So let's go through this as a bit of revision as well. So the probability that x is greater than or equal to 50. Don't forget the binomial CD can only do less than or equal to. So greater than or equal to 50, I want 50 included. So I want 1 minus everything less than or equal to 49. So again, if I do that on my calculator, binomial CD this time because it's an inequality. It's a variable because I know the value of x. X is 49. N is 100. Probability of success is 0.4. So that's going to give me 1 minus 0.972900, which is 0.0270. 9, etc. Okay. So again, not too bad. It's an approximation. It's not brilliant, but it's not too bad. And the approximation will get better the bigger n is, and definitely the closer this probability of success is to 0.5. Okay, I'm just going to get another piece of paper to do part C. Okay, part C then. We want the probability that x is less than 35. First thing we need to do is our continuity correction. So let's think about our number line. So 35. I want to be less than 35. So this is what I want. If If I'm going to do by my binomial then, less than 35 means less than or equal to 34, so we can check that in a second. From a continuous point of view, less than 35, I'm going to go lower than 34.5 here to get my continuity in there. It's a continuous variable now. So my normal variable, the equivalent, is going to be less than 34.5 because that will get me the same values, same part of this that I wanted. Okay, and again, let's do that. So normal CD. My lower value now, I don't know, so I'm just going to put in something really low, minus 1,000. Actually, put a bit too much in there, doesn't matter. As long as it's more than 5 below, we're fine. 5 standard deviations below the mean. Upper value now 34.5. Sigma root 24, mu 40. And I'm getting my answer 0.13078. Okay, if I'm going to check it using my binomial, probability that x is less than 35 is equivalent to the probability that x is less than or equal to 34, and I've got to have a less than or equal to do my binomial CD, so let's do that. So 34, 100 and 0.4 from the question, 0.13033, etc. And again, not a bad approximation here, and it would be better particularly if the probability of success was closer to 0.5. So that's the idea of using a normal distribution to approximate a binomial distribution. So that's the end of that video. Watch the next video now for a more challenging question that involves standardised and normal as well.